Swayam Prabha. Digital India. Educated India.
Welcome. Till time we have seen that if we want to use Rankine cycle as the prime cycle for electricity generation, then what would be the different attachments so that we can improve either the efficiency of the cycle or increase the power or work output of the cycle. But as it is told, our major focus here was to generate either mechanical energy at the outlet of the shaft or electrical energy through the generator connection. So that was the prime motive, and in that motive we worked out, and then we saw that okay, superheating is necessary, reheating is also essential, and we can do regeneration for increment in efficiency. But it is not always that we are primarily interested in the electricity generation. We might have some other requirements, or we might have steam available for other requirements, or we might have the steam produced which is used for some other purpose. So if such is the condition, then what to think about having Rankine cycle with us. So in that, first topic to discuss is the back pressure turbine. First point to be discussed. So we know that we have steam available with us, and we have seen that we use the fact that our Rankine cycle is condensing type turbine. So our Rankine cycle has a turbine which is attached with a condenser. So we have steam at the inlet to the turbine, then we have power output from the turbine, then we have steam outlet from the turbine passing to the condenser, and in the condenser we have cooling water going in and cooling water coming out. This cooling water is specially from the natural resources, as what we have said earlier. So this cooling water will take the heat from the steam, and due to this heat transfer we get saturated liquid water at the exit of the condenser, and then that will be circulated. So this type of arrangement is what we are calling now as condensing type of turbine. But we might have a situation where we are having steam as a constant temperature bath. Basically steam, as what we know, the steam inside the dome is having constant temperature and constant pressure. So if at all we have heat transfer from such a steam which is there where we are having dry plus wet liquid water available, and then such steam is a very good constant temperature source. But such constant temperature source is very much required for various applications in the industries like paper, textile, jute, rice, sugar mills. So in such cases we need the wet steam for, or dry saturated steam for various drying or other applications. In such case we are saying that okay, if we are having steam available, then that steam initially we would pass through a turbine, we will have some power output from the turbine, and in the exhaust we will give that steam to the required industrial process. We will not let that steam to go to the condenser. So we will not have heat released to the atmosphere, but we will have heat going from the steam which is used for the purpose which is a process in any industry. So here turbines are used to drive the to deliver steam as well as power output. So basically turbines are giving the steam at required pressure and temperature for the process. Further, they are also giving us the power output. Here steam is useful for heating or drying applications, as an example of district heating, petrochemical industries or process industries. So these are the some basic applications where we need steam as a source of heat. So how would it be comprised? The process is very simple, the cycle is very much same. We have 1 to 2 as pumping process, then we have 2 to 3 where we are adding heat into the boiler, we have 3 to 4 we have turbine which will produce work output. From 4 to 1 we are replacing the existing condenser by a process heater. So we are saying that the condenser is getting replaced by a process heater. Then we have the TS diagram for us, where 1 to 2 is the pumping process, 2 to 3 is the heat addition in the boiler, 3 to 4 is turbine, and then 4 to 1 is a process where we are releasing heat, and that heat is getting released for process heating. So this is how we are presently thinking, and such turbine in which exhaust is supplied to the process heater instead of a condenser is called as back pressure turbine. Here we know that QH, which is the heat released for the process heating, is basically Ws into H4 minus H1. So here we are purposely saying that Ws is the amount of mass flow rate of the steam through the circuit, such that this unit is in terms of watt. Then we have Ws is equal to mass flow rate of a steam, which is equal to QH upon H4 minus H1. This Ws is basically a calculation which is required for a thermal engineer to know, since this QH would be known in watt for us, which is required wattage for the heating purpose, and this is the enthalpy drop by the steam in the heating process. So this much mass flow rate is sufficient to supply this much wattage of thermal energy. But along with supply of this steam for QH heat process, we are having Wt as the turbine work output, and that is H3 minus H4 into Ws. Then we have turbine output in terms of kilojoule per hour, where we are just replacing Ws by this formula, which is QH upon H4 minus H1. Then we can find out efficiency, but here we are saying that this efficiency is called as cogeneration efficiency, and this cogeneration efficiency is practically Wt, which is calculated turbine work, plus QH is the amount of heat given for the process in the process heater divided by heat supplied. So this is what we are having efficiency in such case where we are using the back pressure turbine. This efficiency is not termed here as thermal efficiency, but it is called as cogeneration efficiency. Here, if plant generates electricity and also provides heat for the process, then such plant is called as cogeneration plant. Basically, we are saying that we are not solely producing electricity, but we are doing some process which is an essential process for the industry, which is something like paper industry, jute industry, sugar industry. So that process is also getting done. We are also generating electricity. So we are doing two things, and it's a cogeneration, and that's why such plant is called as cogeneration plant. But if process heat is major motive, then such power plant is called as byproduct. But if we focus mainly upon process heating and then not major amount of electricity generated, or focus is more on the process heating, and such power plants, such plants are called as byproduct plants. In the same line, we have next turbine, which is called as pass out turbine. The thing to be remembered in last case where we are talking about the back pressure turbine, so here this process is happening in which we are supplying certain amount of heat for the process, So the pressure at the exit of the turbine is not generally below the atmospheric condition, since the temperature, general requirement of temperature is above 100 degrees Celsius. So a process needs high temperature steam, which is a constant temperature source, so that steam will be available if we work about the pressures which are higher than the atmosphere pressure. So back pressure turbine will have exhaust pressure generally more than atmosphere. So such turbines where exhaust is given more than atmosphere and the steam is used for the process is what we are calling it as back pressure turbine. But now we are seeing that there is a pass out turbine. What we are seeing over here is, it's a simple process what we did it for the regeneration case. We are having turbine which is executing a process 3 to 5 for expansion, but in between in the state 4 we are taking W amount of steam as a bleed, and this W amount of bleed at state 4 is taken at the desired pressure for that process. So if we want steam at 2 bar, then we will take the extraction at 2 bar. If we want steam at 5 bar, then we will take the extraction at 5 bar. So this 4 state is dependent upon the saturation temperature which is required for the heating process, and then this steam is used in the process heater, which earlier case we were using in the feed water heater to heat the water which is getting supplied to the boiler. After process heating we will get saturated liquid, and that saturated liquid will be pumped forward as what we do in case of pumping forward regeneration case, and that water will mix with the water which is pumped from 1 to 2 in the condenser pump, and then the mixture will retain the state 8. Here pumping is between 6 to 7, then 7 state is mixed with 2 state, and then we have 8 state. Then from the state 8 to 3 we are having boiler, and we have condenser between state 5 to state 1. So here our major aim is producing electricity also along with the process heating. So we don't have only heating as process heating as the major motive or equal motive as electricity generation, but we have the basic idea that we will generate majorly electricity also, and partially we will give some steam for process heating. Such cases we call it as pass out turbine. Then our TS diagram is like this, where we now are saying that Ws is the amount of steam which we are supplying to the turbine, and then there is expansion of Ws, but we are extracting at this saturation point for 4, and then this is going to give the latent heat for process heating. So this QH is for process heating, and then we are having this to be pumped forward. It is going to mix with the pumped condenser pump, and then we are having state 8, and rest of the things are same. We are taken W as amount of bleed for the process heating. Now we can do the same calculation where we are saying that Q1 is equal to Ws into H3 minus H8, and then we have Q2 is equal to Ws minus W into H5 minus H1, H5 minus H1. This is the heat lost to the atmosphere. Q1 is the heat gain in the boiler. Then we have QH is W into H4 minus H6. This is the amount of heat given for process heating. Then we have turbine work as usual. Initially we have Ws amount of steam getting expanded from 3 to 4, but we have Ws minus W amount of steam getting expanded from 4 to 5. We have pump work which is Ws minus W plus basically we have pump work for this drip kind of pump where we have W amount of steam getting pumped from H6 to H7. So we have H7 minus H6. So this is the total pump work. Then we have Ws minus W into H8 minus H2. This is the increase in enthalpy of the water. Water will increase its enthalpy from 2 to 8. From 2 to 8 water is increasing the enthalpy, but we are having W amount of steam which is also changing its enthalpy from H7 to H8. Practically, in other case, what we were writing was we are having W minus Ws amount of water at H2 state that is mixing with W amount of other water at H7 state, and both are mixing, and then we are forming Ws amount of water at H8 state. So, what we will have is W into H2 minus Ws into H2 plus W into H7 is equal to Ws into H8. So, we have W into H2, we will have okay. So, here we are writing the energy balance for the liquid mass of water which is getting mixed between the two states 2 and 7, and then it is forming 8. That is what we are writing, that Ws minus W amount of water at state 2 is mixed with the water which is at 7 state, and then it is changing its enthalpy to 8. So, this is the rise in enthalpy of the water which is moving from here to here, but this enthalpy rise is due to enthalpy loss of W amount of water which is coming from H7 to H8. So, this is loss in enthalpy by one water, this is gain in enthalpy of other water, and this is what we were saying in earlier case, that we are having W minus Ws minus W amount of water at state 2 which is mixed with W amount of water at state 7, and then we have Ws amount of water at state 8, and then this after rearrangement will give us same equation as what we are writing over here. So, this is the energy balance to obtain state 8. So, this will be helpful to find out Q in. So, Q in is equal to Ws into H3 minus H8. So, this is the basic formula for pass out turbine. Now, we are going to the next point where we are thinking that since we have either we have the case of actual regeneration, or we might consider that there is a pass out turbine where we are taking the bleed for process heating. So in these cases we are taking bleeds. But if we are thinking that we are supposed to work with regeneration as a major reason for which we are basically targeting improvement in efficiency of the steam power cycle, in such case where we should take the bleed from the turbine expansion process, that is what we are calling it as optimum regeneration pressure. So we are supposed to find out what is the optimum pressure for regeneration. So as what we know, we do regeneration in the expansion process from 6 to 8, where we take bleed at 7, but we are arguing at this moment in this expression or in this derivation that we can have 7 pressure like this, we can have pressure 7 like this. So we can have pressure 7 existing anywhere along this vertical line 6 to 8, but which would be the optimum, means which would be the best condition for the extraction or bleeding the steam. And for that, let us consider that M1 amount of mass is taking in bleed from 7 state, and this M1 amount of mass is in losing its enthalpy from 7 to 3, but that enthalpy was useful, that loss of enthalpy was used to gain in enthalpy for 1 minus M1 mass of liquid water from state 2 to 3. This is the energy balance for the regeneration. This helps us to find out M1. M1 is equal to H3 minus H2 divided by H7 minus H2. Now we will take some assumptions in that very first fact, which we will consider as what it is generally said, that H1 is equal to H2. Pump works are negligible. Similarly, H3 is equal to H4. So this practically we say that pump work is negligible. Having said this, then we can put this over here, and then we can say that M1 is equal to, here H2 is replaced by H1, so H2 is also replaced by H1. So H3 minus H1 divided by H7 minus H1. This is what M1. Now efficiency is equal to 1 minus Q out upon Q in, where Q out is 1 minus M1 into H8 minus H1 divided by H6 minus H4, that is Q in. Now we are going to replace here this term which is 4, since we know that H4 is equal to H3. So this formula numerator will remain same, 1 minus M1 into H8 minus H1, but its denominator now will be H6 minus H3. So if we put now M1, which is M1 here, then we will get a new formula where 1 minus term which says that 1 minus H3 minus H1 divided by H7 minus H1 into H8 minus H1 divided by H6 minus H3. Then this after rearrangement leads to H7 minus H3 into H8 minus H1 divided by H7 minus H1 into H6 minus H3. So this is the formula for efficiency. Now this is the formula for efficiency, same formula as what we have till time derived. Now we will take certain assumptions over here. We will assume here that the turbine line follows a path such that H minus HF is constant. Now we are here, so this is H on this line. So if we are here, so we are saying that H7 minus H3, and this is equal to, now this is A, and then this A will go to this B. So this is HA minus HB. Otherwise, if we would have taken regeneration over here, then this is C to D. This is equal to HC minus HD. So, the H on this line minus corresponding HF on the blue line of liquid saturation point is constant along the turbine expansion. So, we are calling it all the terms as beta. All these are beta for us. Now, let us assume that the enthalpy rise in feed water heating, which is H3 minus H2, is equal to H3 minus H1, and that is gamma. So, heating which is happening in the feed water heating is said as gamma, and this expansion process enthalpy difference is said as beta. But this beta is a constant. This is an assumption and rather observation. So, if I write H7 minus H1, we are trying to express every term in this expression with respect to these beta and gamma. We are saying H7 minus H1, but this can be written as H7 minus H3 plus H3 minus H1. So, but H7 minus H3 is beta and H3 minus H1 is gamma. Similarly, H6 minus H3 can be decomposed into H6 minus H5, H6 minus H5, 5 is a saturation point, H5 minus H1, H5 minus H1, this is 5 here, this is 1 here, minus H3 minus H1, minus H3 minus H1. So, this term is beta, this term is alpha, and this term is gamma. Here we are defining that H5 minus H1, which is the saturation enthalpy corresponding to liquid saturation point of boiler, and saturation enthalpy corresponding to liquid saturation point for the condenser, and then that is a constant. Since we have defined boiler pressure for our power plant, and we also have defined condenser pressure for our power plant, and then we are finding what is the optimum 0.7 for bleeding. So, for that our this pressure and these pressures are known. So, this point and these points are known. So, their enthalpy difference is a constant, and that we are calling it as alpha. So, this expression says that H6 minus H3 is beta minus gamma plus alpha. Then we can write our efficiency formula as 1 minus beta means beta square divided by beta plus gamma into beta minus gamma plus alpha. Then here we are seeing that beta is a constant, here we are saying alpha is a constant. So, only variable is gamma, and that gamma is the actual feed water heating enthalpy difference, and then that for that optimum case it will be leading to maximum efficiency. So, we are interested in finding out maximum efficiency for a given gamma. So, we are saying that in the efficiency formula we are only having gamma as variable. So, we are differentiating efficiency with respect to gamma. Then we are getting a formula like this, which we are equating to 0, and this lead to gamma is equal to alpha by 2. And as what we know, alpha is the enthalpy difference between boiler saturation enthalpy of water liquid and the saturation enthalpy of condenser liquid water divided by 2. So, we have gamma is equal to alpha by 2 means enthalpy rise in one feed water heater is half the total enthalpy rise which is going to take place between boiler and condenser. In our derivation we have considered only one feed water heater, and this expression is for only one feed water heater. So, for one feed water heater if we want to put, then it has to be put at the intermediate level, at an intermediate level between these two saturation conditions. So, enthalpy rise has to be half, and so since enthalpy rise is to be half, we are saying that corresponding temperature rise should also be half in the feed water heater. So, for that we are saying that delta T in the feed water heating or temperature rise is basically half of boiler minus condenser saturation temperature. So, this formula is basically for corresponding alpha value. If we put corresponding gamma value, if we put as alpha by 2 in this formula, then we get a formula for efficiency, which is new efficiency with optimum regeneration state. So, this is change in efficiency which we are interested in. So, for that this efficiency formula is without regeneration. So, this is change in efficiency in the presence of regeneration, and here we can see that alpha is appearing in square, this term is in square, and further beta and alpha, they are also positive numbers. So, this efficiency is a positive number, this efficiency change is a positive number. So, we always get gain in efficiency. So, having said that, with change in the efficiency being the positive number for consideration of regeneration, now let us see that if we have many regenerations or many feed water heaters, then how can we find out more than one case. So, let us see that delta T is the overall temperature difference, which is the temperature difference between boiler saturation temperature and condenser saturation temperature. So, as what this figure says, one is the temperature maximum at the entry of the boiler, at the entry of the turbine, 2 is at the exit of the turbine, 3 is at the entry to the pump, and G is the saturation temperature for the boiler, and F is the entry to the feed water heater. So, feed water heating is between Fg, feed water heating is from 3 to F, and Fg is the economizer. Okay, feed water heating is from 3 to F and Fg is the economizer. So, enthalpy rise in the feed water heater is now said to be Hg minus H3, Hg minus H3. We are neglecting the minor temperature rise in the economizer, and then we are seeing that Hg minus H3 is the temperature rise in the in the feed water heater divided by n plus 1. That gives us the enthalpy rise in one feed water heater. So, if there are multiple feed water heater, then what will be the enthalpy rise in one feed water heater? So, that enthalpy rise would be actually Hg minus H3 divided by n plus 1. Then here n is the number of feed water heaters and 1 is the economizer. So, total rise in enthalpy, if we are having n feed water heaters, then that will be n into rise in temperature for one feed water heater. So, it is n into Hg minus H3 divided by n plus 1. So, total temperature rise by n feed water heaters is n into delta T divided by n plus 1. So, now if we have 0 feed water heaters, then we have 0 temperature rise. If we have 1 feed water heater, then it is delta T by 2. So, in the same manner, now if we are having this as the temperature difference between the boiler and the condenser, then their saturation temperature, then we will install the feed water heater here, which is delta T by 2. Now, if we are having 2 feed water heaters, then we will decompose this temperature difference, which is saturation temperature of the boiler and saturation temperature of the condenser, into 3 parts, and then we will send M1 and M2 masses in the 2 feed water heaters such that we will get the optimum efficiency. So, if there are 4, then the absolute temperature difference between the boiler and the condenser would get divided into 4 parts, equal parts, and then we will send M1, M2, M3, and then accordingly we will do regeneration, which would lead to maximum efficiency. So, if we are having n is equal to 1, we have delta T feed water is 0, if 2 it is delta T by 2, and if it is n is equal to 2, if we are having 2 regenerations or 2 feed water heaters, then the total temperature rise. So, we initially are here, at the entry to the pump. So we are here at the entry to the pump. So now this is the total temperature rise which we are expecting. It is divided into 3 parts, 1, 2 and 3 parts. So we want to have maximum efficiency, so we have divided it into 3 parts. So we say as per this formula that 2/3 temperature rise means from here till here the temperature rise will be done by feed water heating and rest temperature rise will be done by the economizer. Same thing in case of 3 feed water heaters, the whole temperature difference will be divided into 4 parts, and then we will have the feed water heating till the third part of this 4 part case, and then we will have economizer. So it will be like this. So this is what we were talking about, having energy efficiency increment due to the regeneration or feed water heating if we are implementing an optimum case. So if we want to see what is the cycle efficiency with number of feed water heater, then this is how we can see that cycle efficiency gets increased with increase in number of feed water heaters. So this is what we say that delta N1, when we had 0 feed water heaters, then we went to 1 feed water heater, so this is delta N1. So if we move from 1 to 2 feed water heater, then this is delta N2. If we move from 2 to 3, then this becomes delta N3. So this is what we are having jump in efficiency. So now if we are here 6 and 7, then we can see that there is negligible change in the feed water heater based change in efficiency. So it is logical that we should not implement too many feed water heaters. 5 to 6 feed water heatings are sufficient to get the change in efficiency. There onwards we would not have much change in efficiency. So this is how we end up our discussion on the process of regeneration, where we have seen that how to implement the regeneration process in a steam power cycle, where we can improve the efficiency and we can basically implement different number of or different types of feed water heating system, where we have closed type of feed water system, we have open type of feed water system, where we have seen that if we are going to do only electricity generation, then there are certain cases, but if we are going to do for the cogeneration or if we are going to do for process heating, then how regeneration comes into picture for back pressure turbine or also for the bypass turbine. So we will see the next part in the next class. Thank you.